You have a choice. Choice 1, quantum mechanics.
This is my brain, and this is quantum mechanics.
In the real world, this food processor is called a double-slit experiment, consisting of a particle gun, say an electron gun over here, a barrier in the middle which has two slits in it, which is why it's called a double-slit experiment, and a wall upon which a pattern can appear. Now the crazy quantum mechanics hypothesis, it's insane, is that particles and waves both go in this direction. Now if this were a gun shooting bullets, most of the bullets would be stopped by this barrier in the middle, but some would go through each of these slits, and what you would get over here on the target screen is two vertical lines. If, on the other hand, this were all fluids like water, the waves would go through these two slits, and over here on the target screen, it would cause a wave pattern. The reason this double-slit experiment plays such a central role in quantum mechanics is because when you fire subatomic particles, such as, say, electrons through here, they go through this barrier somehow, and they form a wave pattern over here, which basically makes no sense because you would think of them as being particles like bullets, and you would not think of them as causing a wave pattern. Now, if I were to count on my fingers all the insane ideas that flow from this, I would need more than just these fingers. I would need my toes also to count how many contradictions arise. Nobel Prize winner Richard Feynman said, "This is the central mystery of quantum mechanics." Well, if dozens and dozens of contradictions arise from this assumption that waves and particles go in the same direction, why not, at least once or twice, entertain the opposite possibility, that the waves go one way and the particles in the opposite direction? But no one, not even Richard Feynman, who was actually a pretty bright guy, no one has ever thought of that. Choice 2, the theory of elementary waves, TEW. I love apple pie. Now, the nature of wave equations in mathematics is that the equations are the same whether the waves go in this direction or this direction. And so, why not try it the other way around? Say that the waves are coming in this direction and the particles in this direction. So here are the rules of the game. Every point on the target screen emits waves. They go through the two slits. Wave interference is located over here. There is no wave interference at all over here. When the waves impinge on the electron gun, the likelihood of an electron being fired in response is proportional to the height of the incoming wave, which is determined by the interference that just occurred. If a wave does trigger an electron, it will follow that wave and that wave alone back through either one of the slits, it doesn't matter which one, and hit precisely that point on the target screen from which its wave originated. Once the electron is fired, there is no further interference, and the probability of it arriving at that spot from which its wave came is 100%. So it turns out that this mechanism I just described leads to precisely the same pattern on the target screen and exactly the same mathematics as does the quantum mechanical model. And this model, unlike the quantum mechanics one, is possible if you allow for zero energy waves, which I will describe in the fourth video, TEW4. Since this model I'm describing is not the one taught in science class and is unusual, I will have to describe a little bit what the effect is of waves coming from different points on the target screen in terms of the likelihood of them triggering an electron to be fired to follow the wave back to exactly that point from which it came. We'll start by examining a point in the center of the target screen. It radiates waves out. Some of them go through the upper or the lower slit. The waves through the upper and the lower slit interfere with one another as they impinge on the electron gun, and since they are in phase, you have peaks adding to peaks and valleys to valleys, constructive interference, a high likelihood that an electron will be fired in response, and therefore a high likelihood that a dot will appear in the center of the target screen in response to that wave. Now let's consider the elementary ray coming from a point just slightly higher up on the target screen. It's so arranged that when the waves come out from there, the peak of one wave hits the upper slit just as the valley of the other wave hits the lower slit, and vice versa. Thus they are out of phase. When they go through the two slits, they're out of phase. Over here, the peaks of one wave add to the valleys of the other wave. There's more or less flat water. The waves cancel each other out. Since there's no amplitude of interference, therefore an electron is not going to be fired, and therefore there's no dot that appears on the target screen at that point. That area of the target screen remains white. Now let's consider elementary rays originating from a point just slightly higher on the target screen. From this point here, as elementary waves go out, the peak of one wave will hit one slit just at the same time as the peak of a different wave will hit the other slit. And similarly also when the valleys go out, they're exactly one wavelength apart. They go through the two slits in phase. There's constructive interference, a lot of amplitude, and therefore a high probability of an electron being fired, and thus a high probability of a dot appearing on the target screen at that point, and therefore we will put a dark area in there. This way of thinking that I've just presented is very strange. Let's ask, how do I see my hand? Some people would have said that photons come into my eyes. Others would say that waves come into my eyes. Quantum mechanics would say that wave particles come into my eyes. Our theory says that elementary rays go out from my eyes and photons follow them back. Now what does that mean? Does that mean that I have light beams coming out of my eyes? No, not at all. There are elementary waves everywhere. They're coming from my shirt and my skin, and the photons from the lights are following them back, which illuminates my shirt and my skin. They're coming from that camera that you're watching me through, and they're hitting my shirt and my tie and my skin, and photons from these objects are following those rays back into the camera, and that's how you see me. It's admittedly a very strange way of thinking. So in summary, I've shown you a way in which we can explain the double-slit experiment without any need for wave particles. The waves are just waves, the particles are just particles. Ask any quantum expert on Earth how to wrap your mind around the double-slit experiment, and they will tell you you have to put your brain in here. But just in case you are reluctant to do that, I have an alternative suggestion for what to do with this apple. Turn to your TEW cookbook, open it to the page about baking an apple pie, peel your apples and slice them carefully and put them in a bowl, mix them up following the instructions written here, and then carefully put them into a pie crust. Preheat the oven to 390 degrees Fahrenheit, 200 degrees Celsius. Put the pie on a flat cookie tray and put it in the oven to bake for 50 to 55 minutes. And then we take the pie out. It's got quite a bit of juice here. It's bubbled out onto the tray. We'll move it over here onto the table so I can show it to you. So in my opinion, this is a much better thing to do than putting your brain through a shredding machine. But then again, that's just one man's opinion.